So you've probably played around with large language models like ChatGPT. I mean, they're everywhere, and they're fantastic at generating all sorts of text. But what happens when you need more than just a plausible-sounding answer? Today, we're going to look beyond that, at a new frontier in AI designed for really high-stakes problems, where being correct isn't just a nice-to-have, it's absolutely everything. And this quote right here, it just hits the nail on the head. When we're talking about critical stuff like designing a computer chip or programming a robot for surgery, you can't just cross your fingers and hope the AI gets it right. No way. You need a system that can actually plan, check its own work, make revisions, and only then give you the final answer. It's the huge difference between a confident guess and a provably correct solution. All right, so how do we actually get there? Here's our game plan for this explainer. We're going to start with what's called the correctness crisis. Then, we'll reframe how we think about reasoning itself, seeing it as a form of planning. We'll dig into why LLMs, for all their strengths, kind of struggle with this. After that, we'll introduce a really powerful new solution. And finally, we'll see how this is all being put into practice right now. Okay, let's dive right in with the central challenge. How do we build AI systems that aren't just fluent and sound smart, but are actually, factually and logically rock solid? This right here is a really fundamental shift in thinking. The best, most reliable AI systems aren't just one single giant model. They're what we call compound systems. You can think of it like an expert team. You've got one person generating ideas, another person whose entire job is to check for mistakes, and a third person who refines the work. It's a loop, a process, exactly how a human expert would tackle a really tough problem. Now, to really wrap our heads around this, we need a new way of thinking about AI reasoning. Let's stop picturing it as some kind of magic black box. Instead, let's start seeing it as a careful, step-by-step process of planning. And the key concept here is something called reasoning traces. These are basically the building blocks of a solution. Think of it like in math class when the teacher told you to show your work. That's what these are. They're all the little intermediate steps, defining a term, setting a smaller goal, doing a quick calculation, that build a clear path from the problem all the way to the solution. This lays out that path perfectly. You start with the problem, you generate an intermediate plan using those reasoning traces, but here's the absolute game changer. That validity check. You have to be able to stop in the middle of your work and ask, hold on, am I still on the right track? You have to be able to do that before you get all the way to the end. Because without that midstream check, you're just stuck in this super frustrating loop of guess and check. Imagine you're building a massive bridge. What if you could only find out if the design was stable after you laid the very last brick? If it collapses, you have no idea what went wrong. Was it the first support beam, the fifth? You just have to tear the whole thing down and start over from scratch. It's just incredibly inefficient. So this brings us to the tools we all know and use, large language models. And look, they're amazing at what they do, but their core design, the very way they're built, creates some serious roadblocks for this kind of rigorous check-your-work reasoning. Let's break down the three big ones. Yup, there are three fundamental problems baked right into the DNA of LLMs that make this whole verifiable planning thing a real uphill battle for them. First, they're autoregressive. That's a fancy way of saying they generate answers one piece of a word at a time, in a straightforward line. If they make a mistake early on, they can't just go back and fix it. It's like talking and not being able to correct something you misspoke a sentence ago. Second, they're locally scored. This means they're trained to just predict the very next word that's most likely. They're not trained to make sure the entire paragraph, the whole argument, is globally correct. And third, they're discrete. Their output is made of these fixed blocks called tokens. This makes trying to do a small, precise edit incredibly clunky. It's like trying to perform delicate surgery with a giant wrench. So, if LLMs aren't really the right tool for this job, what is? Well, this is where the hero of our story comes in. Energy-based reasoning models, or EBRMs for short. And they are designed specifically to overcome these exact weaknesses. The secret sauce behind EBRMs is this really elegant idea called the energy score. It's simple. The model assigns a single number to any plan or reasoning trace. If the score is low, the plan is good, it's consistent, it's correct. If the score is high, it means something is broken. It's like a built-in quality control meter. So let's put these two head-to-head. Remember how LLMs are autoregressive, stuck generating things one token at a time? Well, EBRMs are non-autoregressive. They can generate and look at the entire reasoning trace all at once. This is a huge deal because it means they can flexibly revise any part of the plan at any time. Okay, next up, where LMMs are locally scored, just obsessed with predicting the next word, EBRMs are globally scored. That energy score we just talked about, it evaluates the quality of the plan from start to finish. This makes sure the entire argument is coherent and hangs together, not just the individual sentences. And finally, while LLMs are stuck working with those clunky discrete tokens, EBRMs work in a continuous space. What that means is they can make incredibly precise surgical edits to a plan. So instead of that wrench we talked about, they have a scalpel. This lets them make targeted refinements instead of just clumsy rewrites. Now, this all sounds great in theory, right? But is anyone actually doing this? Is it being put into practice? Oh, absolutely. So for our last section, let's take a look at how a company called Logical Intelligence is turning these powerful ideas into real-world tools. They've built a system that has two main components, and these two are designed to work together perfectly. Meet Kona and Aleph. First up, you have Kona. The best way to think of Kona is as the core reasoning engine. It is the EBRM we've been talking about. It's the part that learns that all-important energy score to figure out if a plan is good or bad. And it turns out it's especially good at complex tasks that involve spatial reasoning, not just language. And then you've got Aleph. Now, if Kona is the powerful engine, Aleph is the brain. It's the sophisticated orchestrator of the whole system. Aleph is the coordination layer that manages all the different pieces. It knows when to call on Kona's heavy-duty reasoning, when to use an LLM just for its language skills, and when to pull in other tools. It's the conductor of the whole orchestra. And the proof that this works? When they put it to the test, Aleph got a near-perfect score on something called Putnam Bench. This isn't some easy test. It's a notoriously difficult benchmark for formal mathematical reasoning. So yeah, this isn't just theory anymore. This approach is delivering state-of-the-art, verifiable results. All right, so let's wrap this up with the key takeaways. First, the best way to think about complex AI reasoning is as a form of adaptive planning. Second, LLMs, for all their power, have three key limitations that hold them back from doing this well. Third, energy-based reasoning models, or EBRMs, solve these problems using a global energy score. And finally, systems like Kona and Aleph from Logical Intelligence are proving this isn't just science fiction, it actually works. And that leaves us with a really fascinating question to think about. LLMs have given us this incredible, easy-to-use interface to talk to AI. But for the really deep, complex, high-stakes thinking that we'll need in the future, are EBRMs the powerful, reliable engine that's actually going to get the work done? It's a powerful idea, and it could very well define the next chapter of AI. Thanks for tuning in.